The vast majority of groups we have studied so far have been abelian. In particular, cyclic groups are abelian. Because in a cyclic group, every element is a power of a fixed generator, and powers of the same element commute. However, non-abelian groups play a very important part in group theory. In particular, historically, groups arose in the context of studying symmetries, and today they also play a very big part in studying symmetries. And in fact, the first important family of non-abelian groups that we're going to introduce has to do with studying symmetries of regular polygons. So we'll start with an example and consider symmetries of a square. So here is a model of a square, and I actually drew 4 axes of symmetries of this square. But before we get to these axes, let's actually consider certain other symmetries of the square, which are rotations. So what do I mean by symmetry of a square? So imagine that I place my square here into this square on the board. And the symmetry of a square is an operation I'm going to do to the square. I can lift it, I can do whatever I want with it in the air, okay? And then I place it back here. And then I see what happened to the vertices, how they have been moved. And all possible such moves constitute symmetries of a square. So first of all, if I start with a square like this, the first thing I can do is, if I want to lift it, I can rotate it by 90 degrees. Actually, we're going to do rotation counterclockwise by 90 degrees. And if I put it back, you see it fits exactly into that form. However, of course, the vertices have now changed. You see the vertex A that was right down here is now here, which I denoted, which I drew over there. Right? The vertex B got moved from here to here. It's right there now. So that's B, that's C, and that's D. Okay? And I denote that rotation by 90 degrees counterclockwise by R. What else can I do? Well, I can move it. I can actually rotate it by 180 degrees. Which is the same as doing the rotation by 90 degrees twice. Once, twice. You see, it's a symmetry of a square because if I put it back, it again fits into this shape. What happens now to the vertices? Well, A went up here, B is up here, C is down here, and D is down here. So that here is rotation by 90 degrees counterclockwise twice. Let's just write this down here. So R is rotation by 90 degrees counterclockwise. I can continue with these rotations, right? I can now rotate it 3 times counterclockwise by 90 degrees. If I rotate it once, I get this one. If I rotate it again, I get this one. And I rotate it again, and I get this one over here. DC is here, AB is here. So that one here is rotation counterclockwise by 90 degrees 3 times. What happens if I rotate it even more, 4 times? Well, look, once, twice, 3 times, 4 times, I get back to the same rotation. So, I get back to the same shape. So, in some sense, that's like rotation by nothing, R to the 0, which means do nothing. What happens if I rotate it 5 times? Well, not surprisingly, once, twice, 3 times, 4 times, 5 times, I get the same thing as I would have gotten if I rotated it once. So I do not create any further symmetries by rotating it by more multiples of 90 degrees. But there are other symmetries of a square, and that has to do with these lines drawn here. Namely, look at the horizontal line. So my A and B are at the bottom, and so my C and D are at the top. So if you look at the horizontal line that cuts the square exactly in half right here, I can do a flip like that. Okay? So that, again, gives me a symmetry of a square. Because I start with this, I lift it, I do a flip, and I put it back in. What happened to the vertices? A went up here. Sorry. No, my picture is not really... Yeah, no, my picture is good. So A went up here. There's B. there is, no, my picture is not good. Sorry, I should start like that. A, B, C, D. Okay, so what happened now? A went up here, there's B, there's D, and there's C. So I get that. Right? I start like this, A, B, C, D. I rotate it around the horizontal axis that goes to the middle of the square, and I get CD at the bottom, AB at the top. So I denote this by F with a little horizontal stroke. So F like this means flip with respect to the horizontal axis of symmetry. Okay, but there are other flips possible, right? I can use the vertical axis and rotate it like this. So that's that flip. The vertical axis goes through here, so that replaces C and D switch places and A and B switch places. And then there are these axes that are diagonal. So I can, for example, hold these two and rotate the square like that. So if I hold it like here, then D and B do not move, and A and C switch places. So D and B do not move, they stay where they were, and A and C switch places. So that's a flip with a little slanted stroke like this, indicating this axis of symmetry. And finally, I can do this with respect to that axis of symmetry, so then A and C stay put, and D and B switch places. Okay, so what is a symmetry then? From that point of view, it's a function. It's a function on the vertices of the square. So it takes the vertices of the square and somehow changes their positions. So a symmetry. So a symmetry of a square is a function from the set of vertices of the square to itself. Right? So, so what does rotation do to A? Well, it maps it to where B was, and so on. Okay? I'm not allowing the vertices to be mapped wherever they want. This symmetry has to be realizable this way, that when I lift the square, I'm able to do something in the air with it and put it back down, this gives me back a square, right? So for example, what I cannot do is I cannot keep these two fixed and just switch C and D. There's no such symmetry of a square that leaves these two vertices unchanged and switches these two. So it's a function, not every function, it's a certain function. So the functions that we allow can be realized by lifting the square of the ground, moving it in 3D without stretching or tearing, and putting it back down. It's sort of awkward to give a very precise definition of these symmetries, while I think it's very easy to visualize what they are when you actually try to perform these symmetries on an actual square that you cut out of the piece of paper. Okay, so these are all the symmetries that you can get from a square. So these symmetries a group under composition. So as functions, they can be composed. And in fact, if I compose two symmetries, I get a symmetry of a square. Because, I mean, that's really obvious, right? If I start with a square and I do something to it, I'll lift it off the ground, I do something, and I return it down. Then I lift it again, and I again do something. I don't know how crazy that is. I put it back down. Then I could have just lifted it, done the first thing, then without putting it down, do the second thing, and then put it down. That's the same thing. So that's also a symmetry of a square. So symmetries form a okay. So symmetries can be composed. And why do they form a group under composition? So let's think about it. What do you have to prove that something is a group? So first of all, the operation has to be a binary operation. So that means if I take two symmetries and I compose them, I again get a symmetry. But we just discussed this. That is clear. If I lift a square, do one symmetry, and then do the other one without putting it down, that's still a symmetry. Those two done consecutively still give you a symmetry of a square. So the symmetries, the composition of symmetries gives you a binary operation on the set of symmetries. What else has to be true? That composition has to be associative. But we already discussed this. Composition of any functions is associative. So in particular, this one is also associative. What else has to be true? There has to be the identity. So there has to be a symmetry such that any symmetry composed with that symmetry gives you the original symmetry. You see, I specifically wrote down here this one, do nothing symmetry. Because if I take any symmetry of a square, any one of those, and then after that I do nothing, then I get the symmetry I did in the first place. So the do nothing symmetry plays a role of the identity. And finally, inverses. Okay, so let's check that inverses, that every symmetry has an inverse. But you see, even without checking every element, that's clear as well. Because if I take my square and I lift it and I do something with it, I don't know, maybe flip it, rotate it, then how do I know that this symmetry has an inverse? I'll just do these movements backwards and I get my original square. So doing these movements backwards is also a symmetry. So clearly every symmetry has an inverse. Okay? So without writing this all down, let me just say that the symmetries form a group under composition. This is called the dihedral group. Dihedral group of order 8. Of order 8 because it has 8 elements, denoted by D8. All right, so let's now list the elements of that group. So what is in D8? So D8 consists of the identity, which is do nothing. Then I have R squared. You see, I initially wrote R squared without explaining why I'm putting a square there. But it's really just a composition of counterclockwise rotation by 90 degrees with itself. So that's why it makes sense to put R squared there. And this is R cubed. And then I have 4 flips. It's a group of order 8. Let's learn a little bit about the elements of this group. So first of all, let's compute the orders. So of course the order of the identity is 1, nothing to compute there. What about R? How many times do I need to apply R to get the do nothing? Not so surprising, right? If I start with a square and start rotating it by 90 degrees, am I doing it counterclockwise? No, I guess this will be counterclockwise. Once, twice, 3 times, 4 times. So R to the 4th is the same as the do nothing. So 4 is the order of R. What about R squared? Well, R squared rotates the square by 190 degrees. I don't know how to stand. Okay. 180 degrees. 180 degrees. Okay, and I'm back to doing nothing. So R squared, I need to do only twice to get to the identity. So the order is 2. What about R cubed? Alright, I'm not going to be rotating this because I'm going to get lost. But if I rotate the square by 270 degrees, then I get this. If I do it again, that's rotating it by 540 degrees, which is the same as 180. So you do not get identity yet. Rotate it again, and you get what? You get 540 plus 270, so that's 810 degrees. It's still not a multiple of 360. But do it again, and finally you get the do nothing transformation. So the order here is 4. What about the flips? If I flip this, if I flip the square once and then again, I come back to the original square. So the order of every flip is 2. Okay, so we've got orders of every element. Now let's check if the group is abelian. First of all, look, I mean, it has, when you look at these rotations, if I compose any two rotations, then of course I do get that they commute, because powers of the same element commute. But let's compose a rotation with a flip. So let's do R composed with vertical flip, and then vertical flip composed with R. And the question mark is, do we get the same thing? Okay, so let's do this on the pictures. So I start with A, B, C, D. And all right, so I'm doing this. So I first do vertical flip, which means I'm flipping it with respect to this axis, right? Vertical flip. So C and B go here, and A and D go here, right? Flip it like this. A goes to A and B switch places, C and D switch places. Now let's do rotation 90 degrees counterclockwise. So A goes up here, D goes here, C, D. Okay, so this here is rotation composed with the vertical flip. Now let's do it in the other order. So first I want to do rotation. Counterclockwise 90 degrees. So A goes here, B, C, D. And then I want to do the vertical flip. So if I do the vertical flip, A and D switch places, and B and C switch places. So this is what I get. Did I get the same thing? No, I didn't, right? The result is different. The vertices got permuted in a different way. So this is not true. So because I found one pair of elements that do not commute, that immediately means that the group is non-abelian. So D8 is not abelian. Not abelian. We can actually identify which elements these two things give us. So, okay, so here's this one, and the black one is here, right? This was F composed with R. And what are these things? So R composed with F1, let's see, from this to that, which one is it? So I have to have C here, so it's C, D up here, look, C, D, A, B. That thing is a flip with respect to this diagonal line. What about this thing? So from this triangle I get AD, so it's AD at the bottom, I'm looking for AD. Here, AD at the bottom, BC at the top, so it's this. So this thing here is the other flip. Yeah, so you see composing rotation by 90 degrees counterclockwise and a vertical flip in two different orders give you two different elements. Maybe just some other things you might want to see or might want to think about or consider inside D8. There are actually lots of subgroups you can consider for D8. So I can look at the subgroup generated by R. That is automatically a cyclic subgroup. What does it consist of? All the rotations. So the rotations form a cyclic subgroup of D8. Inside this subgroup I have another subgroup generated by R squared. So that's E and R squared only, right? Because the next, if I square this, I get R to the fourth, which is the identity. So that's a cyclic subgroup inside. The flips, each of the flips, for example, gives you a cyclic subgroup that consists only of the identity and that flip. So there's actually lots of interesting subgroups inside the group of D8. So this is an example of a group that really arises by studying symmetries of something. You, of course, don't have you don't have to study symmetries of a square. You can study symmetries of other regular polygons, and that gives you the general dihedral groups. So the smallest dihedral group you can possibly have is when you study symmetries of an equilateral triangle. How many symmetries can you have here? Well, you can rotate this guy. So I can do rotation by how much now? Rotation counterclockwise by, well, 120 degrees this time, right? Because again, these vertices have to cover the original ones. So you get, when you do this, B goes up here, C goes here, and A goes here. So that's R. If you do the rotation twice, you get rotation by 240 degrees. A goes here, B goes here, and C goes here. R cubed, of course, is the identity, right? So there is, of course, the do-nothing symmetry. But then you also get three axes of symmetry here. They're not like the ones in the square. They are like you drop a height from a vertex onto the opposing side, and you get three axes of symmetries. So you get three flips here. So in this notation, it will be like the vertical flip, the flip like this, and flip like that. So what do you get? So if you do vertical flip, then C stays the same and A and B switch places. If you do flip with respect to this axis, then A stays the same and C and B switch places. And the flip with respect to that axis, B stays in place and A and C switch places. So the dihedral group of order 6 has 6 elements: E, R, R squared, flip, vertical, and 2 diagonal flips. So in general, a regular n-sided polygon has exactly 2 n symmetries. Half of these symmetries are rotations. So the identity rotations by a multiple of 360 degrees divided by n. In this here, right, n was 3, so it was by 120 degrees. In the case of a square, n was 4, so that was 90 degrees. In case of a pentagon, you of course get 72 degrees. So you get r squared, r cubed, r to the 4th, and then they do nothing, the identity. And n flips with respect to n axes of symmetry. And these axes come in 2 different types, depending on whether the polygon has an even or an odd number of vertices.